intended for this summer school has landed into the program of Distinguished International Conference. Therefore, I a little modified my presentation and like to go a bit broader view on the nano research in our city of Tartu. And to start with, but there will be a few words about nanotubes too. To start with, our university is quite old one, operating since 1632, well, with some breaks, of course, in between. And our faculty is by far the largest in the university, including 6 institutes and our Institute of Physics. As to our institute, some general data, 2,500 employees. It was bigger in the mid of 80s. It was 3.5 and so, but then it was reduced immensely and now increasing again. You see some numbers and some teaching related things. Now as to the structure, you can get general ideas about the topics or what are studied or what are dealt with. And I'll go into a bit more details with laboratories relevant for our conference, I mean in nanoscience and nanotechnology. There is this laboratory of laser spectroscopy. Me and Leonid here are representing, which is historically has been for a long time in optics and optical spectroscopy. You see some important keywords: single molecule spectroscopy, hole burning in the past, and nanos as a nanoscience, plasmonic phenomena we are dealing with and contributing to this project, and all kind of nanoparticles. This is what you call zero-dimensional nanoscience. Then there is a laboratory of physics of nanostructures. I will give you some more details about these ducts. Nanowires, solid gel technologies, and one important, I think, keyword, nanotoxicology. It's a becoming more and more important topic, and we are starting to work on it with collaboration biologists in medical people, in people from other institutions in Estonia. Then laboratory of thin film technology, and mainly this is atomic layer deposition. Quite an advanced method to grow thin films, and by the end of 90s they were quite advanced in growing hafnium oxide and things like films like these, what now already are used in Intel chip nanotechnology. No time to go into details. And then perhaps also laboratory or biophysics. Biophysics is a broad field, but we are dealing with photosynthesizing systems. Primary steps in photosynthesis, energy transfer inside these antenna complexes, and what's unique here, we have unique combination of high resolution laser spectroscopy, high time resolution spectroscopy, high spectral resolution, hole burning, fluorescent line narrowing, and in acidation, high pressures. Not so high as to for the people dealing with diamond anvil techniques, but so still several tens of kilobars, and you can see interesting effects in such systems. So then laboratory of X-ray spectroscopy, which is mainly of interest for its connections to big international facilities. Just now there is going on construction in Lund of new synchrotron radiation source, where we got money for constructing and building a special Estonian beamline, and also a new neutron source in there. And then, of course, we can't go without theoreticians. We are quite a strong group of theory of solid state. You see the number of different topics they are dealing with: superconductivity, nonlinear dynamics of optical crystal, of crystal lattice and vibronic solitons, vibronic electron interactions. In the past, they have contributed to the theory of resonant secondary emission, and of course had quite close collaboration with experimentalists from spectroscopy. Now, as to the big facilities, we have got using, well, thanks to European money, some quite good equipment. Recent years is a double beam scanning electron microscope plus focused ion beam, Helios Nanolab. Next year we hope to purchase transmission electron microscope, then surface science station, then micro-Raman, microluminescence spectrometry, and what's for physicists perhaps the most important, and to testify that we have in the field last April there was quite a big conference on nanotechnology organized in Tartu. Traditionally this was a conference kept by Latvians, but for the first year they decided now we'd be for 1 year in Estonia, 1 year in Latvia. 250 participants from about 20 or so countries. Perhaps even some of you have been there. Sure, our people from Tartu have, but I don't know. So next year it will be in Latvia, then again Estonia. So keep your eye on this conference. It may be worth of coming. This conference photo is taken in front of our science center of Tartu. Science center mean, you know this place is like exploratorium in San Francisco and other places. We have such a nice place in Tartu by now too. Okay, and that was the most important for physics. Just now there is going a construction of a new building. So if you come to visit us in a year or so, we hope to receive you already in this new building. It's located in the forming university campus, and then physicists from different locations in the city, who by now are separated, move all into the same building to join this teaching and science and all into one. Okay, and just to go fast through some slides illustrating different topics in nanospectrum, in nanoscience we are doing within a project or center of excellence. Nanocrystals may have specific pentagonal shape which is incompatible with translational symmetry, but that they managed to do this, and then of course there arise strong deformations and you need defects like dislocation. Then it's just practical things, so gel things for different applications, tubular, growing tubular oxide structures. Then composition glasses, you can use, manipulate their transparency using applied electrical field. Then nanomanipulation and nanomechanics, I would say, nanofriction and vibrations of nanorods, nanotubes. As I said, our landmark is optical spectroscopy, particularly impurity spectroscopy, now combined with effects you can get in plasmonics. Okay, and pulse laser deposition. Also some modeling of nanosystem and structures, including graphene, Azerbaijan graphene. Well, I need to do a few words about nanotubes. Why tubes are good? You see it's well known, not only cylindrical symmetry, flow of fluids, and they are light and rigid charges. You know this is formula for the twist rigidity. Okay. It's not so bad, no good with the flowing tubes. The same horsepower, it now works in opposite direction. In the sense that biggest volume goes in the outermost layers, but they are the slowest. But the big surprise for flowing nanotubes was that the output throughput was orders of magnitude larger than expected from classical theory. And it turned out that it goes this way, that at the contact, this liquid simply slips along the wall of tube. It's not the zero velocity, it's much higher. And this gives you the big throughput. Now, it should be that it was intended as a lecture, and in the lecture we asked questions. What do you think, when were the first nanotubes synthesized? Just some suggestions.
Around 1980s?
Yeah, some more perhaps.
1954.
Sorry?
1954.
Ah, now it depends. But they are real nanotubes, which you can find all biologically, not all biological, but in the cells of multicellular organisms. And they carry some essential functions, cell division, intercellular transport, and so. And they are very interested in the particular systems. There have been even been speculations that a very functioning brain may be based on some quantum resonances in this microtubule, on all this habitual structures. Well, you see, external diameter 25 nanometers is a real nanotube. But compared to, say, to carbon nanotubes, they are very unstable. And this is the very principle of their operation. They grow and decay. It just was all orchestras all was this process in cell division and so. Interesting enough, you can use some simple mechanical models to explain their operation and their instability. No time to demonstrate this by now, but in general you can get a lot of insight into what goes in on nanoscale. From, I would say, on methods of continuous media or engineering and so. You can downscale it to quite small dimensions, at least get some heuristical ideas how things could operate and what could happen there. Okay, and then some more effects perhaps related to nanotubule in biological cells. Which means that apparently it makes sense for physicists to give more attention to them and study all the interesting processes. You see, this temperature is quite close to our body temperature. Well, some more tubes from Tartu. I showed you already, which you can, not nanotubes now, it's microtubes. You can grow from some by solid gel method. By different methods, further pulling your sol liquid with its sol and then polymerizing it, or the polymerization of the surface of your sol, and that's the cracking of the forming layer of gel, and then rolling it into tubular structures. And to finish with, most of or many of us are lecturers, and we need to impress our students. A good way to impress your students, if you like, you are dealing with this self-organization and growth of systems, to show them such a simple experiment. You take a water solution, say of sodium silicate. It's water soluble, you can buy it at construction shops, I guess. And so then you drop it the tiny pieces of salt crystals, salt which are solvable in the water, but silicates of metal which are insoluble. And then you immediately see the start of growth of wonderful, depending on this, of course, the salts is made of different structure, different color, and so. Now, if you like to get the explanation, I can get literature source. Take or find the novel by famous German writer Thomas Mann, a Nobel Prize winner, Dr. Faustus. And there on a full page, you get quite a detailed description of this experiment, down to the chemical names of all compounds, what are needed, and so on. I guess that's all. Thank you for your attention.
Thank you very much, Professor Kikas. Now the paper is open for a question. We have a few minutes.
Okay, you mentioned about nanofriction. How do you measure nanofriction of nanowires? How do you measure nanofriction in nanowires?
Atomic force microscopy. Yeah.
Other questions?
I will be around, so anyhow.
I have a few.
Yeah.
When I said 1954 was the carbon nanotubes, is a paper published in Russian, so you can read. I can read.
Yeah.
And there is a famous discussion about the invention of carbon nanotubes.
Yeah,
and so
yeah.
on. But what is your view of nanotubes, carbon nanotubes and nanotubes in general, and on the application? Because concerning carbon nanotubes, we are mostly, from the research point of view, working on single-wall nanotubes. While on the other hand, applications are looking for multi-wall nanotubes. So what is your view in single-wall, multi-wall? What are the perspectives?
My view as to the, so to say, robust application to tune mechanical properties of materials, makes them of higher strength, and though then there perhaps there is no need for single wall, and so then so multi-walls are quite okay. As to the electronic and such application, but which in fact are much more distant as to the commercialization, and that so there of course you need single wall nanotubes, but to my understanding the crucial point is defects. Defects in nanotubes as a thing to graphene, defects in these structures, which is because for electronic applications you need quite ideal structures, no defects, and I think this is a main obstacle we have to fight and to learn about how to manipulate and reduce perhaps the structures, or put just structures of needed configuration and needed geometry into these structures.
Are there any other questions? Please.
I want to ask you about the defects maybe in carbon nanotubes. What type of carbon nanotube, single wall or multi-wall, has more defects in general?
Oh, this is now a specific question. I must admit that I'm not specialist in carbon nanotubes. It's not just my field. It's more optical spectroscopy, and so I guess you may know a better answer yourself than I have.
It all depends on the production strategy and the purification processes. You can say a priori what is if one kind of nanotubes are more or less defective than the other. Okay, if there are no other questions, please thanks Professor Kikas again.